Researchers observe atomic-scale rainbow scattering in graphene for the first time. Researchers at the University of Duisburg-Essen and Uppsala University, led by Carolyn Frank together with Professor Marika Schlieberger and Professor Daniel Primet-Sofer, have experimentally observed rainbow scattering in ion transmission through single-layer graphene, a phenomenon that had previously only been predicted and simulated, never directly measured. Atomic rainbow in graphene image. Rainbow scattering is a well-known effect in classical scattering theory, arising when particles following different trajectories converge onto the same characteristic angle. It appears in contexts ranging from ordinary rainbows to nuclear and crystal scattering, and it encodes detailed information about the interaction potential between a projectile and its target. Applying this to graphene had been an attractive but elusive target. Capturing the effect requires both an extremely clean, defect-free single-layer graphene sample and a detector with very high angular resolution, since even minor surface contamination smears out the pattern. The team accelerated xenon ions to 40 keV and transmitted them through freestanding single-layer graphene, using the time-of-flight medium-energy ion scattering TOFMI setup at Uppsala University. The resulting scattering pattern showed two distinct features: a sharp circular outer rainbow at a scattering angle of 5.28 degrees, produced by the kinematic limit of close binary collisions between individual xenon ions and single carbon atoms, and a hexagonal inner rainbow at 0.43 degrees, arising when ions pass through high symmetry regions of the graphene honeycomb and are deflected slightly by several carbon atoms at once. Only the combination of the ultra-clean graphene sample from Duisburg and the exceptional resolution of the measurement system in Uppsala made this observation possible, said Carolyn Frank, first author of the study and a doctoral researcher at both universities. The scattering pattern is highly sensitive to even small amounts of surface contamination, which explains why it has not been reported before. The researchers compared their measurements against molecular dynamics and binary collision approximation simulations using several established interaction potentials. While the models reproduced the outer rainbow well, they showed clear deviations from the measured data for the inner hexagonal pattern, particularly at the smallest deflection angles near 0 degrees. The team attributes this to the limitations of commonly used radially symmetric potentials, which fail to capture effects such as non-radially symmetric chemical bonding and charge exchange between the xenon ions and the graphene lattice. Graphene serves not only as a target material, but also as a particularly sensitive testbed for models of ion-solid interactions, said Professor Marika Schlieberger, co-author of the study. Because the material consists of only a single atomic layer, even subtle differences between experiment and theory can be detected. Shop graphene at Amazon.com. Beyond confirming a long-predicted effect, the results establish graphene rainbow scattering as an experimental benchmark for refining interatomic potential models used in ion-solid interaction physics. The researchers plan to extend the approach to other ion species and to two-dimensional materials beyond graphene, such as transition metal dichalcogenides, to gain further insight into the fast dynamics governing how energetic charged particles interact with atomically thin matter. Source: Carbon. www.uni-do.de. Posted, Aug 11, 2026 by Ronnie Peleg.